In this video, we will discuss Poisson probability distributions. A Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. The random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some other similar unit. The probability of the event occurring x times over an interval is given by the formula P of x equals mu to the x times e to the negative mu all over x factorial, where e is Euler's number, approximately 2.71828, and mu is the mean number of occurrences of the event in the intervals. Requirements for the Poisson probability distribution. The random variable x is the number of occurrences of an event in some interval. The occurrences must be random, the occurrences must be independent of each other, and the occurrences must be uniformly distributed over the interval being used. Properties of the Poisson probability distribution. A particular Poisson probability distribution is determined only by the mean mu. A Poisson distribution has possible x values of 0, 1, 2, and so on with no upper limit. For the 55-year period since 1960, there were 336 Atlantic hurricanes. Assume that the Poisson distribution is a suitable model. First, find mu, the mean number of hurricanes per year. The Poisson distribution applies because we are dealing with the occurrences of an event, hurricanes, over some interval, a year. The mean number of hurricanes per year is mu equals the number of hurricanes divided by the number of years, which is 336 over 55, which is 6.1. B, find the probability that in a randomly selected year, there are exactly 8 hurricanes. That is, find P of 8, where P of x is the probability of x Atlantic hurricanes in a year. Using the formula for the probability of an event occurring x times over an interval, the probability of 8 hurricanes in a year is as follows, with x equals 8, mu equals 6.1, and e equals 2.71828. P of 8 equals mu to the x times e to the negative mu over x factorial, which is 6.1 to the 8 times 2.71828 to the negative 6.1 all over 8 factorial, which is 1,917,073.13 times 0.0022428769 all over 40,320, and that is about 0.107. The probability of exactly 8 hurricanes in a year is P of 8 equals 0.107, a little more than 1 in 10. C, in this 55-year period, there were actually 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in part B? Does the Poisson distribution appear to be a good model in this case? The probability of P of 8 equals 0.107 from part B is the likelihood of getting 8 Atlantic hurricanes in 1 year. In 55 years, the expected number of years with 8 Atlantic hurricanes is 55 times 0.107 equals 5.9 years. The expected number of years with 8 hurricanes is 5.9, which is reasonably close to the 5 years that actually had 8 hurricanes. So in this case, the Poisson model appears to work quite well. The Poisson distribution is sometimes used to approximate the binomial distribution when n is large and p is small. One rule of thumb is to use such an approximation when the following 2 requirements are both satisfied. Requirements for using Poisson as an approximation to binomial. N is greater than or equal to 100, and n times p is less than or equal to 10. If both requirements are satisfied and we want to use the Poisson distribution as an approximation to the binomial distribution, we need a value for mu. That value can be calculated by mu equals np. In the Maine Pick 4 game, you play 50 cents to select a sequence of 4 digits, 0 through 9, such as 1377. If you play this game once every day, find the probability of winning at least once in a year with 365 days. The time interval is a day, and playing once each day results in n equals 365 games. Because there is one winning set of numbers among the 10,000 that are possible, the probability of a win is P equals 1 over 10,000. With N equals 365 and P equals 1 over 10,000, the conditions N is greater than or equal to 100 and NP is less than or equal to 10 are both satisfied. So we can use the Poisson distribution as an approximation to the binomial distribution. We first need to find the value of mu. Mu equals NP equals 365 times 1 over 10,000. We get 0.0365 or 365 10,000ths. Having found the value of mu, we can proceed to find the probability for specific values of x. Because we want the probability that x is at least 1, we will use the clever strategy of first finding p of 0, the probability of no wins in 365 days. The probability of at least one win can then be found by subtracting that result from 1. We find p of 0 by using x equals 0. Mu equals 0.0365 and e equals 2.71828. P of 0 equals mu to the x times e to the negative mu over x factorial, which is 0.0365 to the 0 times 2.71828 to the negative 0.0365 all over 0 factorial, which is equal to 1 times 0.9642 over 1, which is 0.9642. Using the Poisson distribution as an approximation to the binomial distribution, we find that there is a 0.9642 probability of no wins. So the probability of at least one win is 1 minus 0.9462 equals 0.0358. We use the binomial distribution. We get the probability of 0.358. So the Poisson distribution works quite well here.